Welcome to an example on how to set up the limits of integration for a triple integral. Here we're given the region T is the tetrahedron with the vertices shown here where we have an x-intercept, a y-intercept, a z-intercept, and the origin. So this tetrahedron is in the first octant. We're asked to write the triple integral in this form here, where notice how the order of integration is first with respect to x, then with respect to y, then with respect to z. Let's first take a look at the region T in space. The region of integration is this tetrahedron here, where we have four vertices. We have this x-intercept, this y-intercept, this z-intercept, and the origin. So notice how the tetrahedron is bounded by the three coordinate planes and this green plane. So our first step is going to be to find the equation of this green plane. For review, if we have the x, y, and z intercepts of a plane, we can write the equation of the plane in this form here. So in our case, the plane is going to have the equation x divided by 3 plus y divided by 2 plus z divided by 4 equals 1. Now from here, let's go ahead and clear the fractions by multiplying through by the least common denominator, which is the least common multiple of 3, 2, and 4, which is 12. So multiply through by 12. We can simplify before multiplying here on the left. There's 1 3 and 3 and 4 3s and 12, so we have 4x plus there's 1 2 and 2 and 6 2s and 12, so plus 6y plus there's 1 4 and 4 and 3 4s and 12, so plus 3z equals 12. Which means the region T, the tetrahedron, is bounded by the three coordinate planes, which would be x equals 0, y equals 0, z equals 0, and this plane here, 4x plus 6y plus 3z equals 12. Now going back to our triple integral for a moment, we first integrate with respect to x, so we're going to integrate from 0 to the plane where the equation of the plane must be expressed as a function of y and z, which means we must solve the equation of the plane for x. So solving this equation for x, we would subtract 6y on both sides, as well as subtract 3z on both sides. So that would give us 4x equals 12 minus 6y minus 3z. Divide everything by 4, and we get x equals 3 minus 6/4 simplifies to 3 halves, so 3 halves y minus 3/4 z, which means limits of integration with respect to x are going to be from 0 to v of y comma z, which is really just x, equals 3 minus 3 halves y minus 3/4 z. So this is the first part of our question. And now we still have to integrate with respect to y and then z, which means we now want to find the yz trace. We can find the yz trace by setting x equal to 0. So the yz trace is going to be the region bounded by y equals 0, z equals 0, and this plane here when x equals 0, which would give us the equation 6y plus 3z equals 12. So to graph the yz trace, we want to graph these three equations on the yz plane to determine the bounded region. And write down this to save some time, where here's the yz trace, where here's the y-axis and here's the z-axis. So this side of the triangular region would be z equals 0. This side of the triangular region would be y equals 0. And this side of the triangular region would be on the line 6y plus 3z equals 12. Now we can determine the limits of integration for y. For y, we're going to integrate from y equals 0 to this line here, which must be expressed as a function of z, which means we need to solve this equation here for y. To solve this equation for y, we would subtract 3z on both sides. That would give us 6y equals 12 minus 3z. We divide both sides by 6. And so we'd have y equals 2 minus 1/2 z. which is the upper limit of integration for y. And for our problem, we're asked to express it as u of z. So u of z, which is really just y, is equal to 2 minus 1/2 z. And then for limits of integration for z, which are already given, they're from 0 to 4, and that's because looking at the yz trace, notice how we integrate from z equals 0 up to this high point where z equals 4. I hope you found this helpful.